Welcome back to another lesson in the course of Introduction to Computers. In this course, we are going to cover the fundamentals of how computers work. We started off by defining what a computer is. We talked about memory versus storage. We are going to talk about hardware versus storage and hardware versus software in later lessons and things like input versus output. But this lesson is one of the most important one of them all. This lesson is going to be about how we humans can communicate with computers, and to do this we use what is known as binary. So binary, as I've mentioned in one of the previous lessons, is the language of computers. This is how computers understand what we want them to understand. So anything that we want the computer to do, we have to use binary to convert our instructions into what the computer can understand. So how does this actually work? Now, binary at first can be incredibly overwhelming, and it can just seem a bunch of random characters, ones and zeros, there's a bunch of strings and too much, and it's just a matrix effect. But actually, binary is just two characters. Okay, it's 0 and 1. You take zeros, you take a bunch of ones, you combine them in a unique combination, a unique series, a unique sequence, and you get a different value. And different combinations equal different values. So different combinations of binary strings, so different combinations of zeros and ones equals different values in sort of normal English. And I'm going to go through how this conversion works, and I'm going to sort of build up to that level because it requires some sort of building blocks before we get to the final step. But at the end of this whole binary subtopic, we'll find out how we actually convert normal English characters into what the computer can understand and vice versa. But first, let's go through some sort of characteristics of binary, some language around what we mean when we say different things. So first of all, a single binary digit equals a bit. So whenever we say a bit in binary, it's just a single binary digit, so it's either a 0 or a 1. The reason it's called a bit is because some computer scientists took the words binary digit, put it together to form bit. We love our wordplay, so here we are. Then a pair of 2 bits, so a pair of zeros and a 1, is called a crumb. Okay, so slightly bigger than a bit, but it's not too big. So it's called a crumb. Then 4 bits together, so 4 series of zeros and ones equals a nibble. Again, slightly bigger, but not that big. But then 8 bits together forms 1 byte. And 1 byte is usually the typical sort of 1 unit of data within binary. So whenever we sort of typically talk about binary or storage, we talk about byte. So you might have seen something like gigabyte or kilobytes or megabytes or terabyte, petabyte. All of these use this concept of 8 bits together, which is called a byte. And that's, like I said, byte is typically the sort of 1 unit equivalent of binary information. But before we get into the binary conversions, we need to talk about the decimal number system. So the decimal number system is essentially what we use on a daily basis. If you've taken maths classes somewhere in school or outside, or if someone has ever asked you what's 9 plus 10, you can answer them with some value, maybe, I don't know, 19 or perhaps 21, depending on how up to date you are with the memes. But anyways, the normal maths system that we are most familiar with uses what's called the decimal number system. The way it works is you have a string of characters, right? And these characters can be from 0 to 9. We know that. The numbers go up from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you're given a string of different characters, and you have to convert them into a specific value. How does it work? Now, in this example, you have a 2 in the second position from the right, so that means it's got a value of 20. But if I put that 2 in the first position, so to the most right position, it would have a value of 2. right? So the character on its own doesn't have much of a value, but it's the position of the characters that determines its value. And the way that it works technically, and it's very intuitive because we're familiar with this, but technically the way it works is you take the character and you multiply it by a multiplier, which is in the form of this base 10 system, which is what you see. So base 10, essentially, depending on the position, takes the base, which is in this case 10, and multiplies it, well, not multiply, but puts it to the power of some number, and that number is based on the position. So starting from the right, we have 10 to the 0, then one position to the left, we have 10 to the 1, then one position to the left of that, we have 10 squared, then one left of that, we have 10 to the 3, and so forth. And the equivalent values of these powers can be seen on the screen. So from the right again, we have 1, then 1 to the left is a value of 10, then 100, and then 1,000. So how does it actually work? How do we calculate this? And it's very intuitive, and I know that this might be a bit too simple, but I'm just trying to get across the process, the technical process behind this whole calculation. How do we get the value from the initial input string? We start from the right, we take the character, so in this case we'll start with the 0. We multiply it by the multiplier, right, which is 10 to 0, which it doesn't matter because 0 times anything will just be 0. So we look at the next character string, which is 2. We times it to its respective multiplier, which is 10 to the 1. 10 to the 1 just equals 10, so we do 2 times 10, which equals 20. Then we do the same for the character 4, and because of its third position, it equals 4 times 100. And then we take those individual products and we sum them together to get the final value. So it looks something like this. You have 400 plus 20 plus 0 to equal 420, which is our final value in decimal. So decimal is just a normal sort of number system. So starting from the initial string of characters, we have a final value using this sort of calculation process. And this is how the decimal number system works. Now, let's talk about the base 2 number system. So binary doesn't use that base 10 number system. It uses base 2 number system. We already know binary only has 2 characters, 0 and 1. So a binary input, or a byte, as we've seen before, a string of binary digits, will look something like this. So this is your initial sort of input binary value. So we have something like 0010, 0101. Okay, and we want to convert this into a normal value, like a normal number that we can understand. How do we do this? We use the same process, except for one slight difference, which is that the base is not 10 anymore. It's in fact 2 because we're using the base 2 number system. But everything else works in the exact same way. Okay, so starting from the right, we have 2 to the 0, then 2 to the 1 on the left, then 2 to the 2, 2 to the 3, so forth and so forth. And the corresponding value, starting from the right, is 1, then 2, then 4, then 8, 16, 32, 64, 128. So they're essentially doubling, starting from the right, every time it moves 1 to the left, the position. But to convert the binary string into a normal decimal value that we can understand, we start again from the right using the binary string, the input. We take the first character, we multiply it by the multiplier, do this for all the characters, and then we sum them up to get the final value. So in this example, we would have something like this. So starting from the right, we have 1 times 1, which equals 1. Then one position to the left, we have 0 times 2, doesn't matter, 0 times anything is 0. 1 to the left of that, we have 1 times 4, which equals 4. Then we skip 2 positions, we have 1 times 32, which equals 32. And then in the end, we get 32 plus 4 plus 1, which equals 37. So we took the original binary string of zeros and ones, and we converted it using this same calculation process that we saw in the base 10 or the decimal number system to get the final decimal value of 37. Now to convert a normal value into binary, and if we take it one step at a time, we could convert this 37 into binary. Okay, so now you're starting to see how a computer can take binary, which is its language, convert it into decimal, which is our language, humans, and how humans can take normal decimal language, convert it into binary that a computer can understand. And this is essentially the entirety of the base 2 number system. If you want to get more familiar with this, the best way is just to practice. There are online calculators on websites which can help you convert from binary to decimal and vice versa. So I'd say just practice a bunch of times if you want to get familiar with this entire process. Now we're going to talk about the hexadecimal number system, and this is the last one in this lesson. Don't worry, I'm not going to talk about anything else, any other number systems, okay? But this is important in order to understand how we convert characters into binary. So hexadecimal number system carries out the same calculation process as we've seen before, but this time it uses the base 16 system. So instead of the base 10 or base 2, we have 16 as the base. But other than that, it's exactly the same process. And the main point of hexadecimal system is to make it easier to read binary. So imagine reading a bunch of lines of binaries, a bunch of zeros and ones. It can be confusing. It can be quite complicated. So to make it easier for humans to read, and it's primarily for the humans to be honest, we devised this thing called hex. Because a computer doesn't care. Right? A computer, you just give it a bunch of strings. It's fast enough to calculate it without getting slowed down, and it doesn't get confused as easily as humans do when it comes to these sort of things. But how does it actually work? So hex, let's talk about the characters that you can use in a hex, and just sort of build up from previous lessons. In a normal decimal system, normal number system, we have 0 to 9. In binary, we have 0 and 1. And in the hexadecimal system, we have the following characters: 0 to 9, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and A to F, so A, B, C, D, E, and F. Now stay with me for just a few more seconds. We're going to go through an example, and that will help explain the whole sort of values and how these A to F work. Why do we have characters all of a sudden? But just stay with me for now. So each character in the hexadecimal character set has a specific value associated to it. So 0 to 9 have the associated value of 0 to 9 respectively. So a 4 in hex equals a 4 in binary or decimal. And A to F represent values of 10 to 15 in binary and decimal. So A, the character A in hexadecimal, has a value of 10. B has a value of 11. C has a value of 12. D has a value of 13. E has a value of 14. And then F has an associated value of 15. Okay, and there's a reason why it's 15, because in 4 bits of binaries, you can only have a maximum value of 15. Right, so you can only have 1 plus 2 plus 4 plus 18, which equals 15. And each hexadecimal character represents 4 bits of binary. So if you put 2 hexadecimal characters together, if you get a pair of hex characters, you get 8 bits of binary, which is also known as a byte, which is 1 unit of binary data. Okay, and to best understand this, we have to work through an example. Okay, so let's take an example. So we have the pair A4 in hex. How do we convert this into binary? Okay, so first of all, we split the hex into 2 sections. We take the first character, and you can start from the left or the right, doesn't really matter. Let's start from the left. We take the first character, which is A. we find the associated value of this character, which is 10 as we know, and we take 10 and we convert that into binary. So just 10 on its own in binary equals 1010, so 2 plus 8, right? And if you need some help sort of working out how this calculation works from sort of a normal decimal to binary, go through the binary part of this lesson, so just the base 2 number system part. We go through an example in that section. So what you're doing here is essentially here is you're taking the value from the hex character, you convert it into binary. Once you've done it for the first character, then you take the second character, which in our case is 4, which has a value of 4, and you convert that into binary, which is 0100. So now you have two separate 4-bit binary strings. Okay, one for A, which has a value of 10, one for 4, which has a value of 4. Now, to convert the whole pair of hex A4 into binary, you basically take the two strings and you combine it together. So A, this is the binary string for A, which has a value of 10, goes first because it's the first character, and the binary string of 4 goes second because it's the second character in the hex representation. And then you get the final 8-bit or 1 byte of binary equivalent from a hex pair. And I know this sounds very complicated, very confusing, especially going through it the first time, but honestly, just try it a bunch of times. Practice is genuinely the best way you can understand this. And like I said in the previous lesson, previous section, there are a bunch of websites and calculators online which will help you convert from hex to binary and vice versa. So just go through them, play around with it, and just take it step by step. But essentially, now we know how we can convert something from hex into binary. And to convert that into decimal, we just follow the base 2 number system, and we convert the binary into a normal decimal value. So in order to convert from hex to decimal, we have to convert to binary, then we convert from binary into decimal. And this is how this entire sort of conversion works from hex to normal numbers. Because if you think about it, binary, the main reason why we use hex is to make binary more readable. So in order to convert from hex to decimal, you have to first of all convert from hex to binary and then from binary to decimal. So hex is essentially a shorthand for binary in a very simple explanation. But this is the hexadecimal number, and next we're going to talk about how we convert characters into binary and how we actually do the final conversions. So to convert a normal character, something like hello, right, a word hello, which is made of the characters HELLO, how do we convert that into binary? Or how do we tell the computer that this is what we're trying to get out of it? To do this, we have to use what's called encoding, right? So encoding essentially means you define what the different binary values or the different binary combinations are, and we assign them a different value for the different characters that are permitted. So the characters that we use are the normals of English characters from A to Z of the letters, then 0 to 9, then a bunch of additional special characters, like you can see exclamation mark, you can see at the rate, you can see special keys on the keyboard, so you can see, for example, delete or shift or other sort of combination. So essentially, we create this massive encoding defining sort of library. In this case, we call it a table, and then we use this lookup table to convert from binary into characters and characters into binary. So this table specifically is called the ASCII table. Okay, ASCII is just one way of encoding characters into binary. There are a bunch of others. You have things like Unicode, UTF-8, and so forth, and different types of information has different types of encoding. So for example, for an image, you might have a JPEG or a PNG. For a video, you might have an MP4, and so forth. So different data has different types of encoding systems, and encoding systems are just used to convert from binary to character and vice versa. So on this system, say if you wanted to store something like hello on a Word document, you type in HELLO, and on the computer it would convert those characters using this lookup table into binary. So say if I typed in H, it would find, okay, H has a hex hex value of 48 and a decimal value of 72, and then it would use that hex value to convert it into binary, so that when you then save that document with the character H in the storage, it will store it in a binary form, which is equivalent to the hex value of 48. And similarly, if you have a word saying hello, it would essentially convert the hex value of each of those characters into binary and then store that into the storage. So it's a massive sort of process in itself, and you have to deal with things like efficiency and speed of access and so forth without taking too much space. So it's encoding in itself is a massive area of research, and if you're interested, I would say just try and Googling and try and find out what the different types of encodings are and what the differences are and how they work. And there are challenges on each type of encoding, their benefits and so forth. So it really depends on what the purpose is and what the legacy systems are and how sort of experimental you want to be. But ASCII and a few others are very common, and most computers use these types of encodings. You can get some radical ones, but like I said, most of these have a sort of typical approach that you have essentially a lookup table where you map each possible characters on a keyboard to the equivalent hex and decimal and binary values, and then whenever you have to convert from what the computer stores into what we see or vice versa, it uses the table to get the necessary conversions. And that's essentially how we take binary, convert it into things that we can understand on a daily basis, and vice versa, and how we tell computers what we want the computer to do with what information we give it. So that's all from the binary lesson. Thank you for joining in. Hopefully this was useful. But like I said, if you want to get more practice in, try and find out the online websites and the online calculators that help you convert from one form of number to another. And yeah, just find out more about any particular aspect that you found interesting. But hope you enjoyed the lesson. Thank you for watching. Stay tuned, watch the other lessons, and thanks for watching. Bye.